Hi everyone, welcome back to Operations Research. Today we're going to talk about algorithms for nonlinear programming. Okay, so in this video I'm going to give you an overview, and the later videos will talk about two specific algorithms that can be applied to solve general nonlinear programs. Okay, so we actually spent a few weeks ago to talk about analytical methods for nonlinear programming. So what does that mean? We learned the following things. We are able to check whether a program is a convex program or not. We talked about that the feasible region must be convex, or we are maximizing the maximizing a concave function or minimizing a convex function. Yeah, so we gave you some analytical tools to prove the convexity or concavity. We talked about first order condition, which is necessary for any local minimum or maximum, or it can be sufficient if your function is convex or concave. We talked about the feasibility of stationary points. Typically, if your stationary point is feasible, then it has a high chance to be an optimal solution. Otherwise, you may need to turn it back to another feasible point. You probably want to use Lagrangian relaxation, or in general apply the KKT condition. So all of these are analytical tools that may be used for nonlinear programs. Okay, the reason that we want to have analytical methods is the following. First, we want to analyze a problem and to understand some properties. Sometimes this is very important for us to design algorithms. For example, we may need to know some condition for an optimal solution, something that must be satisfied by any optimal solution. If we can do that, we can eliminate a lot of unnecessary points and focus only on a tiny region of our whole feasible region. Okay, you did see some examples about this. First, we do the analysis and then we design an algorithm. Sometimes we try to obtain an analytical results, and with that we are able to understand the problem or even get some economic intuitions or managerial implications. Recall your memory about, for example, the EOQ problem, or you have the pricing problem, you have the quantity decision problems, etc. In the economics literature or in the operations management or marketing literatures, people do use analytical solutions to understand problems and get managerial implications. Okay, that's why we need analytical methods. However, sometimes analytical methods are just too limited and they are not enough. In particular, if the problem is complicated enough, too many variables, too many constraints with a very specific with some general formats, then we are just unable to use analytical methods to find a solution. If we still want to solve a problem, then typically we rely on numerical algorithms to obtain a numerical solution. This is typically the focus if we are talking about an engineering or science application. So they don't really care so much about analytical solutions. Instead, they want an algorithm that can give them the numbers, give them a solution. Okay? And that's the focus for today. So to apply an algorithm, because this is a numerical algorithm, we need to first get the values of all the parameters in most cases. Otherwise, the algorithm just cannot run. And then we're going to see that at least for the algorithms that we introduced to you, all those NLP algorithms have the following properties or similarities. First, they are almost always iterative. That means I will start at some point, and in each iteration I'm going to move to the next point, and then use the next and use the destination to be the next starting point, and move again, and move again. If you recall the simplex method, it is exactly an iterative method following the same idea, right? Moving from this point to the next point to the next point to the next point. And hopefully we get closer and closer to an optimal solution. Mostly they are repetitive. That means in each iteration there are some steps that need to be repeated in this iteration, in the next iteration, in the next iteration. So in every iteration they are doing the same thing. The only difference is that the starting point is different. Mostly they are somewhat greedy. That means inside each iteration we define something for them to achieve, and it seeks for some best things that is achievable in that iteration. So sometimes they solve sub problems, they solve some optimization problems in each iteration, and hopefully connecting all of them, we get to an optimal solution. Finally, is approximation. Mostly you will see that an algorithm relies on a first order approximation or second order approximation of the original program. We are going to see that. Okay, and of course, even though NLP algorithms are powerful, they still have their limitations. So first, sometimes they may fail to converge. So what is converge? Converge means the algorithm finally get to a solution so that further iterations do not modify the current solution a lot. Typically, when we move along points, if eventually we stop at some point, we say the function or the algorithm converges. Okay, and if a function is so weird that an algorithm cannot even converge, then the algorithm may not be able to return a solution to you. In that case, it's bad because you don't really solve that problem. Okay, NLP algorithms are also limited in the next way, in a sense that it may be trapped in a local optima. What does that mean? Suppose we have a nonlinear program that is not convex, then we may have a lot of local minimum or local maximum, and they do not guarantee to be a global minimum or maximum. In that case, because NLP algorithms, as you will see, mostly are some kind of search algorithms. They try to improve each current solution inside a neighborhood. So eventually they may stop at a local optimal point. And in that case, they will be unable to get out from that trap. And eventually we will return just a local optimum. That's possible. So that's why some algorithms play some tricks to try several local optima. But of course, in this course, we don't have time to talk about all of them. Okay, it typically requires your domain to be continuous and connected. So that's why a nonlinear integer program can be very hard to solve, and we don't touch that in this course. Okay, so today we will still focus on nonlinear programs whose domain is continuous and connected. We will tell you all these difficulties and give you some examples to show them, but unfortunately we are unable to cover those remedies or possible solutions to tackle these problems. Okay, but if you are interested, there are other courses, advanced courses that will teach you this. So in today's lecture, we will focus on nonlinear programs, and today we only focus on unconstrained nonlinear programs. So even if it's unconstrained, it can still be very difficult as long as your function f is weird and as long as you have a lot of variables. We will give you the ideas about those searching algorithms, but we assume there is no constraint, so that we can give you the idea easily. So the general form of our function of our NLP is this one. You see that there are n variables with no constraints, and f is twice differentiable. We assume that f is twice differentiable so that our algorithms later can work. We don't really assume that f is convex. Please pay attention to this. We don't assume that f is convex. So that's why our algorithm may only return a local minimum. Okay? But if we are able to show that f is convex, then an algorithm will most likely attain the global minimum. So that's why analysis is still important, even if you want to use algorithm to solve a problem. If you can show analytically that a function is convex, then that returned solution can be said to be a global optimum. Otherwise, you cannot. Okay? So that's how analysis and the numerical methods need to complement each other. Okay, that's it. Thank you.